Hello and welcome to the 2015 EMC Live Test Bootcamp again. This presentation is an overview of EMC Chambers. My name is Graham Kilshaw. I'm the Chief Media Officer of Interference Technology, and we are the creators of EMC Live. The Test Bootcamp's a one-day event today, focused on the test and compliance side of EMI. Today's other presentations will also cover how to implement enhanced EMI characterization, the limitations of rod antennas, pinpointing emissions at the IC and chip level, and how to choose the right test antenna. So if you missed any of those, just sign up for our Interference Technology newsletter and we'll show you how to get them in the next few days. This webinar is presented by Donnie Gray. Donnie joins us from Atlanta, Georgia today. He received a BS in Mathematics and Economics from Allegheny College in 1984 and an MSCE from the University of Colorado in 1990. He recently joined MVG to initiate the business development strategy and the marketing activities to drive sales in the EMC industry. MVG is Microwave Vision Group, and they've developed a unique expertise in the visualization of electromagnetic waves. MVG offers systems that allow for the visualization of these waves while evaluating the characteristics of antennas and helping speed up the development of products using microwave frequencies. Attendees, before we begin, a few notes for the hundreds of you who've registered today. First, since you're already registered, you'll automatically be sent an email next week when a copy of the recording and the slides of the presentation are available to download. So no need to email us. Second, the presentation's interactive, so please do send in your questions during the course of Donnie's presentation. We'll try to answer as many as possible at the end. In order to send in a question, just use the chat box on the right side of your screen. And if you need to minimize or maximize your screen, use the red arrow in the top right area of your screen. Donnie's presentation will last about 35 minutes, and we'll have about 10 minutes for questions and answers at the end. And now, Donnie Gray of MVG will begin the presentation. Over to you, Donnie.
All right, well, thank you for that introduction, Graham. As he said, I'm Donnie Gray with MVG, and I want to give you a presentation on an overview of EMC Chambers. So it's my goal just to give you an introduction to EMC Chambers and to present some high-level concepts. So the focus, will be on the basics and the fundamentals, and is basically geared for those who are less familiar with electromagnetic compatibility testing. So with that, I'll move into my presentation here. And the first thing I want to do is just give you a little review of what EMC testing or electromagnetic compatibility testing is all about. So boiled down to its basics, you want devices that are going to be sold out on the marketplace. They have to be tested for radiated emissions, the amount of energy that they radiate through the air, and they have to be tested for conducted emissions, the amount of energy that they conduct along some cable, any cable that can be connected to that device. It could be power cables, it could be LAN cables, it could be anything. So we want to test those devices for the emissions that they're putting out, and to be sold out into the marketplace, those emissions have to be below some specified level. That level is dependent on the product, the country in which it is sold, and the standards that govern those products. Conversely, depending on the product and the standards that govern that product, items also have to be tested for immunity to make sure they can withstand some amount of energy that we know is in the environment. And so we want to test that device for its capability to withstand radiated immunity. So we know that there are things being radiated through space that will hit this device. And we want to also test that device to be able to withstand conducted immunity. So we'll inject some kind of energy onto the cables. And again, we want to make sure that that device can survive and operate properly. So that is, in its nutshell, that is what EMC testing is all about. Now, to do EMC testing, we want to do the testing in the appropriate facility. Now, the most common type of facility are shield rooms. So everything is done basically inside of a shielded room. And the goal of a shielded room is just basically we want to keep the energy that is on the outside, and we want to keep it on the outside and keep it from encroaching inside that could interfere with our tests. And the energy is on the inside, we want to keep it there on the inside. So that's what this shielding, these shield rooms do. These shield rooms basically give, there's a basic set of shielding that these shield rooms give. Most shield rooms can most easily provide the shielding. Here are some examples that I'm showing. So like up here on the upper left-hand side, that's an example of a copper screen room. There's another screen room. Here on the bottom, I'm showing just a full metal shielded room. But even anechoic chambers are in and of themselves shielded rooms. So an anechoic chamber will provide shielding, and then attached to those anechoic chambers are control rooms or other rooms to house amplifiers, and often they are also shielded. So when you're doing conducted tests, conducted emissions tests or conducted EMS tests, these are very low frequencies. Basically, the energy is conducted along cables and not much energy is radiated, and so it is suitable to do these conducted tests inside of a shield room. And these conducted tests include transients, and in the vernacular of this presentation, transients refer to things like electrostatic discharge testing, surge or burst, where we vary the electricity and things like that, and we want to make sure that your device survives. So those kinds of tests are conducive to being done inside of just a plain shield room. However, the bulk of this presentation really addresses the anechoic chambers that are required for doing the radiated tests. So when you want to test your device for radiated emissions, or you want to test your device for its ability to withstand radiated immunity, then when you're testing indoors, these have to be tested inside of an anechoic chamber. So basically, we want to be able to reduce the reflections, because that's what we want to do. So let me step back a little bit. In the early days, testing, both for antenna measurements, for example, or electromagnetic compatibility, that testing was done outdoors. For antennas, typically the testing was done, or is still done. You put the antennas high up on a tower or on a mountaintop, and the receive antennas on another tower or another mountaintop, and you have free space, and you're eliminating the ground bounce from the ground. Generally speaking, that's how antenna measurements were done. But electromagnetic compatibility testing, that was done in an open area test site or an OATS. And basically, it's similar to antenna measurements. We have free space on the upper hemisphere, but the testing is done typically over a metal ground plane. So if you can imagine, when you're using a cell phone or driving a car or using some other kind of electronic device, these are being used over different kinds of surfaces. So use them over carpets and wood floors and tile floors and cement and asphalt and metal ground planes and things like that. So in those times, it's just easier to standardize over a metal ground plane. And then when people tested their device at different facilities in different countries, we could standardize because we knew every test was done over a metal ground plane. But testing outdoors has its issues, right? We say that Mother Nature is always on. There's always electromagnetic energy that is out in the atmosphere, and that can interfere with our tests. Additionally, you have reflections from nearby buildings, and there's all kinds of other interferences. So today, we know that with all the electronics that there are many potential opportunities for us to interfere with each other. Because today, everyone and everybody is connected to everything else and everybody else. So there is a large opportunity for us to interfere with these tests. Additionally, if we're out there doing immunity testing over the whole frequency range, we don't want to be generating signals at frequencies that we shouldn't be, especially at high powers. For example, here in the United States, we don't want to get in trouble with the regulatory body like the FCC. So that's another reason to test indoors. Also, if you live up in the north, you know it can be quite uncomfortable to test in the winter. If you lived in Boston or Detroit or Minnesota last year, it would have been very uncomfortable many times, most of the winter, to be testing outdoors. So these shielded rooms or these chambers, these enclosures, help protect you from the weather. And then finally, they can provide security. So, you know, if you can imagine automobile manufacturers and Google and Intel and Apple and companies such as that, they definitely want to hide and have security. They don't want others to be spying on and seeing what they're developing. So for those reasons, it's become more common and definitely well accepted to test do our EMC testing indoors. So in testing indoors, there are many different kinds of facilities that we might choose, and it depends on your product, the standards that govern your product, and the marketplace in which your product is being sold. So on this slide, I'm just showing some examples. This is by no means is this an exhaustive list, but this is the predominant amount of types of chambers that are available. So on the left, you see anywhere from compact 3-meter chambers to fully compliant 3-meter chambers, 5 and 10-meter chambers. You have chambers that are specified for military testing. You have CISPR 25 and ISO 11452-2 that are chambers for emissions and immunity testing for automotive components. You have the ETSI, which is the European Telecommunication Standards, which govern telecommunication devices and intentional radiators, and even full automotive test standards like CISPR 12 that govern the testing indoors for full vehicles. So those are just a sample of some of the types of chambers that exist. Now, most of the time, whoops, I seem to have jumped forward a slide. Let me go back. Most of the time, when we're talking 3 meters or 10 meters or 10-meter chambers, what we're referring to is the test distance. And generally, we're talking about the test distance for the emissions testing. For the most part, the emissions testing and the standards that govern emissions testing govern the size and the absorber configuration of the chamber. So that is why that is the common nomenclature there. These different kinds of chambers, they can be compliance or pre-compliance. So if you have a full compliance chamber, it basically can meet all of the performance requirements, and it's authenticated, your equipment is calibrated, and it means when you test your device, it is authenticated, it is able to be sold out on the marketplace. Pre-compliance is more of testing that is done in the R&D environment, when you're making changes, or you want your device, you want reasonable assurances that your device is going to pass the test when you actually do send it to a fully compliant chamber. So most of these facilities are semi-anechoic, and what that means is the ceiling and the walls have absorber, but the floor is bare. It's just a conductive ground plane. Although there are fully anechoic rooms, and we'll talk about that later. In these rooms, you basically need some turntables and towers to rotate the device that you're testing, and also you need the tower to raise the antenna to different heights, and we'll talk about that. Overall, the most common types of chambers that are sold are the 3-meter compact chambers and the 3-meter chambers. These are the least expensive, so they're the easy-to-get budget. They fit in most of the common buildings and that are already built and existing, where these other larger chambers, the 5-meter and the 10-meter and the full automotive chambers, generally you need a new facility that is built to house these kinds of chambers. So as I said, in the past, the testing was done outdoors in an open area test site. So I show here, this is an open area test site. This actually exists in Liberty Labs in Iowa, and you can see it's just a metal ground plane. There's not many things that are outdoors. It's devoid of buildings. but you can see that there still are trees, there are some hills, there is a building that's behind us that houses the workers and other kinds of equipment from the Liberty Labs facility. So there are some opportunities for reflections. I keep hitting my screen and I apologize for that. Over here where you see these boxes, this has a turntable, so this turntable is integrated right into the metal ground plane. And on the right here you see this is a tower, and this tower can move the antenna from 1, 2, 3, and 4 meters, and also it can rotate the antenna into the two orthogonal polarizations, generally horizontal and vertical polarizations. Now, because we're testing over a metal ground plane, and we know that we're going to get reflections, and those reflections are going to vary depending on the frequency, we want to test at 1, 2, 3, and 4 meters. And that's the reason, is because we know we're getting some amount of ground balance. Now, we talked about the positioners that are required. You need some kind of an antenna, antenna mast or antenna tower. These that raise the antenna up and down and rotate it in polarization. For testing FCC, especially above 1 gigahertz, then generally we use what's called a bore sight mast. That keeps the antenna pointing right at the EUT, and the EUT basically stays immersed in the bore sight or inside of the 3 dB beam width for the most part. So that's a requirement that is specific to the FCC testing. Here we can see two different types of turntables. We have one turntable that would be integrated. It's called a flush mount turntable. It will be integrated right into the metal ground plane. It will be a continuation of the perfect electrical conductor. Below that, we see a surface mount turntable. If you did not have the budget for, or you did not have the height in your facility for a raised floor, then perhaps you would have to consider a surface mount turntable that sits right on top of the metal ground plane. So that's an example of some of the positioners that are required in the EMC test facilities. Now, when we're testing indoors, we want to simulate and correlate our results to an open area test site. So that is why you'll see indoors we still have this metal ground plane, and that corresponds to the metal ground plane that we saw on the open area test site a few slides before. Also, we see that there is absorber and ferrite tiles on all the walls and on the ceiling, and that's because on the upper hemisphere we want to simulate free space, just like the free space that we had on the open area test site. Now, in this particular example, you can see that the ferrite tiles cover the entire set. It completely covers the walls, and there's complete coverage on the ceiling. However, we do not have complete coverage using the foam absorbers. And the reason is this. When you have a 3-meter chamber, or a typical commercial chamber, it could be 3 meter, it could be 5 or 10 meter, or it could be compacted. Generally, the standard defines what kind of performance that we need in this quiet zone. And we can get the performance required. We do not, all we need to do is have the absorber on the back walls and in the specular regions, or the critical regions of the sidewall and ceiling, and that gives us enough coverage, enough decrease in the reflections that we can give you the performance that's required by most of the standards. And this is across the board. Most of the vendors do something like this. So we can most of the time either beat, most of the time exceed the performance that is required, and yet we can save money by reducing the amount of absorber that's inside here. The performance of the chamber depends on a lot of things. Basically what we're doing, let me back up, what we're doing with these ferrite tiles and this absorber is we're decreasing the reflection. And that gives us a greater ability to measure and analyze the direct path, you know, the emanations directly from your device. And that's what we want to do with as little perturbations as possible. So the configuration or the size of the chamber, the absorber that's on there, and the size of our quiet zone all are factors in creating this better performance. So as we'll see on the next slide here, that Well, let me back up and let's define what a quiet zone is. Most of you probably know this, but generally in the EMC community, a quiet zone is defined as some kind of a cylinder. And the diameter of this quiet zone has to be big enough so that it can completely encase the EUT or the largest EUT that you want to test. So there definitely is an interrelationship between the performance and the size of the quiet zone and the size of the chamber and the size of the absorber that's on that chamber. So if you can imagine that the bigger the quiet zone, then the more energy we are allowing to encroach into that quiet zone. So the smaller the quiet zone, then we are taking more advantage of space losses, less energy can get into that quiet zone. If we have a larger chamber and we keep this quiet zone constant, then of course our performance increases because we're taking advantage of space losses. If we want larger absorber, then of course we need a larger chamber so that we can keep the same size quiet zone. So these are all the different parts, the interrelationships that define what kind of performance that you get out of a chamber. And then typically what you want is a vendor that will help you optimize this for your particular budget. So how do we decrease the reflection? Well, most of us are familiar with absorber. Most of the absorber that is out on the market is some kind of carbon-loaded material. Polyurethane is very common, but there's also polystyrene, polyethylene, polypropylene. And then additionally there are thin film materials, but they all essentially work the same way. Basically, they provide a small amount of resistance out on the tip, and then as the electromagnetic wave passes through the material, the resistive material gets larger and larger, and the tiny resistances build up, and that is how we cancel the reflection. Now, the common rule of thumb is that for the absorber to work properly, and this is in the EMC world, by the way, where we need about 20 dB decrease of reflectivity, the common rule of thumb is that your absorber should be about a half of a wavelength. Now, if you consider that we want to test down to 30 megahertz a lot of times based on the standards, at 30 megahertz, our wavelength is already 10 meters long. So for us to be able to get absorber to work properly, it would have to be 5 meters. And you can imagine this would be very difficult for us to do. Your chamber would have to be impractical. It would just be impractical to make a chamber that large. The absorber would be very tough to construct. It'd be very expensive. It'd be very hard to mount on the wall and for it to stay there properly. So for that reason, we combine the absorber and we also use ferrite tiles. So the way that ferrite tiles work is that by virtue of the complex permeability and permittivity, we create a magnetic resonance or magnetic loss as the electromagnetic wave comes through the material. So generally, most ferrite tiles are intended to operate from about 30 megahertz to about 1 gigahertz. The primary zone is basically from 30 megahertz to 300 megahertz. You can see we get about 20 dB decrease in reflectivity or better, depending on where in that frequency range we are. So this can be optimized. You can tune this notch. We can move it left or right if we combine the ferrite tile with certain kinds of dielectric. But in general, this is the typical kind of a curve for the ferrite tile. So what we do is on the final solution, we combine the materials into a hybrid solution. And so how this absorber works is out here at the tip, we want to approximate 377 ohms or air. The electromagnetic wave enters into our absorber. The carbon-loaded absorber is providing more and more resistance as the electromagnetic wave comes down into this absorber. We want the resistances at the bottom of this pyramid to approximately match the impedances in this base, and then we want the base to match the impedances that we're going to see in this ferrite tau, and specifically around 300 megahertz, where the transition, where the electromagnetic wavefront starts to go all the way through the material and see the ferrite tile. So that is basically how hybrid absorber works and decreases the reflections in your room. So now let's get into some of the chambers that are out there. The first type of chamber, the most common types of chamber are probably these compact 3-meter chambers. So by compact, we mean they're smaller than a full compliance 3-meter chamber. You can see if we just go with a compact chamber, it's set generally, and these are general, and most of the vendors have similar sizes, generally 7 meters by 3 meters by 3 meters. The 3-meter height can generally fit into most office buildings in height. And with this, we can get a quiet zone of about 1.5 meters. Now, these compact chambers are called pre-compliance chambers, and the reason is this. According to the standard, we must evaluate the quiet zone. There's a method called normalized site attenuation, and the result has to give us a plus or minus 4 dB variation in that quiet zone. But since these rooms are so small, we are not taking it, we are losing the ability to account for space losses. We're not getting as much space losses, the energy is not spreading out, and more energy is getting into the quiet zone. So below 300 megahertz, we're still getting some pretty good reflections, and below 300 megahertz, we're not meeting the standard. Now, these are still good results. It still allows us to do rigorous testing, but we're not meeting the standard. So this is called pre-compliance testing. Now, this would be very good in an R&D lab, or if you just wanted to make sure that your device could pass before you actually send it to an authenticated test lab, because that's very expensive and you don't want to have to test and retest devices. So generally, because these are short, you cannot fit an antenna tower that can operate up to 4 meters. After all, your height is only 3 meters. So it's commonly accepted to have a shortened antenna tower, and generally the most commonly accepted shortened antenna tower is like 2.4 meters. So in the horizontal mode, you would test with your receive antenna at 1, 2, and 2.4 meters. In the vertical mode, you would test at 1 and 2 meters. You still can maintain the 3-meter test distance inside of this device. And then there's a mini compact chamber. It works pretty much the same as a typical compact chamber, but in the mini compact chamber, you really can't fit an antenna tower. If you want to change the level of your antenna or the height of your antenna, then you really have to do it manually, and it's in smaller increments. So these are examples of some compact or pre-compliance chambers that exist and offer you a different solution. So these would be for lower budgets, or if you didn't have the facility to house a full-size chamber. So you can see a full-size a full compliance 3-meter chamber basically is 9 meters, and you'll get some variation of times 5.6, the 5.4 meter height or 5.8 meter height, and generally you can have quiet zones up to 2 meters in diameter, and a full compliance 3-meter chamber gives you the excellent performance that'll pass the standard over the entire frequency range. So if you had a full compliance 3-meter chamber and everything was documented and you had the right calibrations, then when you tested your device, it would be authenticated to be sold on the marketplace. Now, one thing I didn't say in the back is we talk about 3-meter chambers and 10-meter chambers, and if you're from the antenna measurement world, that generally means your chamber is 3 meters, or 10 meters long. But here you see that our 3-meter chamber is much larger than 3 meters. So what we're referring to by this 3-meter nomenclature here is that for emissions, we're able to test at a distance of 3 meters away. So we want our receive antenna to be 3 meters away from the device that we're testing. So how does a 3-meter chamber end up being 9 meters long? Well, this just gives you in general why we need all that space. So you have a 3-meter distance, that's the test distance. The volume, let's say we have a 1.5 meter quiet zone for your EUT, that takes up space. Your antenna and the antenna tower, it takes up space, so there's another 1.5 meters. You have approximately a 0.5 meter of absorber on all the walls, so that takes up another meter. You want some clearance between your device and the antenna and the absorber because you don't want to couple to that absorber or to the wall, so we want some clearance, and that is how we end up with a 9-meter distance to effect a full compliance 3-meter chamber. Now, there's also a 5-meter chamber, so if you have extremely large EUTs, then you might want to go to a 5-meter chamber. Now, a 5-meter chamber is essentially an oversized 3-meter chamber, and by that I mean you're only really validating that chamber at 3 meters for NSA and SVISWAR. There are no standards that really allow you to to evaluate your chamber or validate it at 5 meters. Although some people do test at 5 meters, and the reason is it's more easily correlated to the 10-meter distance. So testing, trying to sell your products in some countries like Korea, they really want the test at the 10-meter distance a lot more than other countries. In these chambers, you can fit larger EUTs, you can fit larger personnel doors, and often you can have dual masts and test at 3 meters with using dual masts, and that allows you to speed up your test. You can have, for example, one antenna that's in the vertical polarization on one mast, and another antenna that's in the horizontal polarization on the other mast, and you can get both of the orthogonal polarizations at one time. So those are some of the advantages of the 5-meter chamber. And the gold standard of testing is a 10-meter chamber. Like I said, in some countries, they only will accept test results done at 10 meters. It gives you excellent performance over the whole range. You have the ability to have extremely large EUTs and do the testing, extremely large doors, and these are the gold standard for testing. Now, when you're doing radiated emissions above 1 gigahertz, generally all the standards and the distances we were referring to in the earlier slides, I'm generally talking about 30 megahertz to 1 gigahertz. Now, when you test greater than 1 gigahertz, there's too many losses through the cables to really do 10-meter testing. So at these frequencies, we test at 3 meters away, and there's a different method that is now commonly accepted as defined in CISPR 16. It's for evaluating the quiet zone. So instead of normalized site attenuation, we validate the quiet zone using the SVISWAR method. It's a little more stringent than the NSA because we're not just using the free space transmission loss technique. So it's a little more stringent, and because of that, we need absorber on the floor to pass these tests. Now, when you're testing below 1 gigahertz, you generally take this absorber off, and then when you're testing above 1 gigahertz, you put the absorber back in. For testing immunity, it's similar. To achieve the uniform 1.5 meter by 1.5 meter field that is specified in this 61000 4-3 standard, we need to have ferrite tiles on the floor. An absorber goes on top of those ferrite tiles when we test above 1 gigahertz. This patch of absorber is generally 2.4 meters by 2.4 meters. Sometimes it'll be 2.4 meters by 3 meters, but that is a small patch that is required for the field uniformity. So when we take these compliance 3-meter chamber or even the compact chamber, we put this absorber down, we can test at a 3-meter distance, and we can still do compliance radiated immunity testing. Now, those were basically commercial style chambers that we were addressing, the 3-meter, the 5-meter, the 10-meter. They were defined by CISPR 16, but when we do testing in the aerospace industry, for example, RTCA DO-160, or the military, we have a different kinds of specifications. Instead of the performance of the quiet zone being defined, we have the performance of the absorber being defined, and then those standards tell us exactly where that absorber has to be. So generally in these standards, we're testing up close. Instead of 3 meters, we're 1 meter away, and we're testing with higher gain antennas, so that's why we see only partial coverage in one corner and in the back wall. On this slide, I'm just telling you that because of how the absorber is specified, often you can meet the performance with just some truncated foam absorber, and you do not need hybrid, you do not need the ferrite tile. But that has to be tempered with the type of test you're doing. If you want to test down to 10 kilohertz, and you want to be using very, very large antennas or strip lines, then often you want to use the ferrite tiles just to minimize your coupling with the chamber walls. And then here's an example of the one end of a mil standard chamber right here. CISPR 25 is similar in that it doesn't define a quiet zone. It defines the performance of the absorber, and then it defines the configuration of the absorber. So for CISPR 25, essentially you have to put full coverage absorber on all the walls in the ceiling. You cannot have the gaps that we saw in the compliance 3-meter chamber. So this could affect you if you ever want to do testing that's CISPR 25 and full compliance 3-meter chamber. Then you have to have the full coverage, but you still have to have a chamber that can deal with the worst cases of both the CISPR 25 and the compliance 3-meter chamber or CISPR 16 standard. Again, I'm just showing even short absorber can handle the performance specifications in a CISPR 25 standard. And also, the standard specifies not only how far away the absorber needs to be based on your EUT or your test table, but it has to be big enough so that your antenna, your test antenna, is not so close to the floor or not so close to the ceiling or other absorber or the walls. ISO 11452, which is the immunity standard for automotive components, this is very similar to CISPR 25. The differences are because we're testing immunity, generally we're dealing with bigger antennas that can handle bigger power, and because of that, the chambers are typically bigger. But essentially, this is very, very similar to a CISPR 25 chamber. And I was just showing some of the performance that you can get with the various absorbers. Even the short absorber can meet most of these standards. There are things called like fully anechoic rooms. It is defined in CISPR 16, for example, and it's also defined in these ETSI standards. It's an alternative to semi-anechoic chambers. In general, most of the rooms, if they're smaller, they'll tend to the customers will tend to want to have it be fully absorbed. One advantage maybe is that if you have an intentional radiator and you want to do some kind of a radiated performance analysis or some kind of a quasi-antenna measurements, then this can be a better choice. But overall, I think most people are finding that the performance between fully anechoic chambers and these semi-anechoic chambers are very similar, and even the ETSI is starting to move towards allowing and defining semi-anechoic chamber for many of their tests. Vehicle testing, of course, has its own concerns. You have full vehicles, they have to be rotated, you're dealing with extremely large antennas and extremely large vehicles, and you have to exercise and let these vehicles move. So you also need not only very large turntables, but different dynamometers. On this page, I'm just trying to show you from going from a simple turntable to a very complex dynamometer. So we have just turntables here. We have a portable dynamometer that could be on top of a turntable, or a portable dynamometer that's just on an electric ground plane, no turntable. We could have a dynamometer that's built into the ground with no turntable, and we can have a fully integrated turntable and dynamometer. And of course, these depend on what the flexibility and the specs that you have, and of course the budget that you have. And when you're doing full vehicle testing, because they're so large, you're already dealing with extremely large rectangular chambers. But if you also want to combine and do antenna measurement testing, which is common often with vehicles, for example, because there are many antennas that are on a vehicle. If you want to do some kind of a combination test, then you need some kind of a shaped chamber, where a rectangular chamber doesn't give you the performance, because to get the performance it would have to be so large that it's impractical. So we need to steer the reflections away from the quiet zone in some other manner, and we do that by using one of these unique customized shapes. So that is my presentation. I hope it's just, like I said, it's just meant to give you the fundamentals and the basics, and I hope that it'll help you move forward. So I think we still have some time, and I think we can take some questions.
Thanks, Donnie. What a great presentation. Yeah, I think the whole area of chambers is often a misunderstood area. You know, what's anechoic, what's shielded, what's semi-anechoic. I've personally learned quite a bit today. That was great. Let's go to the questions. We don't have too much time left, but we'll try to answer as many of the attendee questions as possible. If you do have any more questions, now's your last chance to send them in. Just use the chat button on the right side of the screen. If anybody's looking for more information on chamber types and the visualization of electromagnetic waves, you can find those at mvg-world.com. So let's go to the first question. This comes from Dmitry Penkin, Donnie, and his question is, well, first of all, he says, thank you for the talk. That's a nice comment. Why, Donnie, why do some absorbers shown have a non-sharp or flat top?
Yeah, well, that's a good question, and thank you for the compliment, Dimitri. Generally, that flat top is used because our frequency is not so high in electromagnetic compatibility. So if we were going to higher frequencies, then we would have to amend that and would have to have a sharp tip. But generally, at the lower frequencies, we don't need quite as good of an impedance match, and we can still get performance. And what that allows us to do is give you more room, more space for a given chamber size inside of the chamber.
Okay, and here's a related question from Taylor Handleton, who's asking, many of your images show a quote-unquote backwards white set of absorbers fitted into the blue absorbers on the walls. I think Taylor's referring to the sort of reverse out shape of the absorbers. Do these serve any EMC purpose, is the question.
Well, I don't know if I can find an example, but typically, here's what we do. The ferrite tiles, we'll panelize them, put it on a wooden board, and then we'll put it up, and it does a couple of things. Number one, it does help the performance. It helps us shift that curve one way or another. But really, the important thing is it helps us be able to more easily mount those ferrite tiles, and then if you ever have to move or reconfigure, it allows us to reconfigure them more easily.
Okay, makes sense. Next question comes from Eduardo Gotti, and Eduardo's asking, this is a really interesting one, what's the method to determine the boundaries of the quiet zone inside a given chamber?
Well, there are a lot of different methods. So basically, you need to know the characteristics of your absorber, and then there's multi-ray tracing techniques. There's all kinds of different techniques that are used to evaluate the quiet zone. And then, of course, over the years, a lot of these sizes and distances are well known because many of these chambers have been installed. They have gone through empirical tests. So besides the modeling capabilities, there's a lot of anecdotal evidence that's out on the marketplace.
Okay, we're going to begin wrapping up. There's actually a couple more questions and comments here, Donnie, and I think we'll answer these online after the presentation today because we're out of time. This is a good one to think about. How are the chambers tested to make sure they're actually shielded from the outside world? But if you want to know the answer to that one, you're going to have to go to the Test Bootcamp website next week, and we'll get Donnie to answer that one there. Nice comment again from Fatih Sahin, who says, thank you so very much for such many useful information. I quite agree. Greg Wilkins asks, is it possible to get a copy of this presentation? Yes, it is, Greg. You're already signed up. We'll be sending it to you and everybody else who registered automatically within the next couple of days. Tony Rule would like to add some applause to the presentation and for the entire day of the EMC Live Test Bootcamp. Thank you for an enlightening experience. Well, thank you, Tony, for the message. We sincerely appreciate it. We hope everybody enjoyed it today. There's one more presentation left today, but first I want to say a big thank you to Donnie for a really interesting, very useful presentation, and to all of his colleagues at MVG as well. The next presentation is the 10 factors you need to understand when choosing the right EMC test antenna. And that's coming up at 3:45 East Coast time in the United States. That's about 30 minutes from now. You still have time to register if you'd like to hear that presentation. I hope you've enjoyed all of the test boot camp today. I'm Graham Kilshaw from Interference Technology. Hopefully we'll see you again in 30 minutes. Thank you.